Now a part has 3 degrees of freedom. So there's 3 translational degrees of freedom and 3 rotational degrees of freedom. Okay, so what I like to think of that here is if we look back at our datum references, this slide right here, a degree of freedom is the part can move along this x-axis in either direction. The part can move along the y-axis, in this case it's drawn up and down, or along the z-axis. And then those are the translational. Okay. Now the rotational degrees of freedom are shown here. This is this W here, so that you can rotate the part about that axis. All 3 of these axes. X-axis has a rotation, y-axis has a rotation. So these are essentially the degrees of freedom. If we were talking a tool design class, this would be the degrees of freedom that must be arrested when you're work holding, fixturing a part. Those are our degrees of freedom. How do we put datums? How do we identify surfaces of datums on drawings? Not just surfaces, but also features of size. Here's how we do it. A datum feature symbol is typically a square containing 1 letter to identify a datum feature. The square is connected by a triangle to a short line to identify the surface or feature of size as a datum. Okay, so we can apply datums to a surface or to a feature of size. So in this example right here, what we've done is we've taken an extension line off of that surface, and then we applied our E, our datum E. So that's an E in a square, typically square box with a short line and then a filled in triangle. So that's one way to do it. There's other ways to do it too. So in this case, what we have is we have a orientation tolerance and datum applied to it. So in this case here, we're applying the datum symbol to a feature of size, in which case what we did is we replaced one of the arrows on the dimension lines with our datum arrow. The other way to do that is to put the datum underneath here, underneath the size call out. So here's how to apply a datum reference, a datum identification to a flat surface or a plane. In this case, we have C. We could put it right on the surface, or we could put it off the surface with an extension line, just like we did the A here, and then the B. So here's how we apply datums to the drawing. Here's how we can simulate those datums. So datum A is this largest surface, and what we have is a plate in a fixture that's used to check parts. Okay, as you can see, the simulator here, it accounts for all the imperfections in your datum A. It essentially sits on the high spots. So datum A, we always say, is supposed to be picked up by 3 points. Okay, so the 3 highest points on the surface of the part become your datum A using this simulator. This simulator also has, we call it a tool here, but it's essentially doing a simulator. It's simulating those datums. It also has a part here that picks up datum C, and it has a part of the tool here that picks up datum B. So this tool, if you will, this datum simulator, it simulates the datums of this part. So that's how we apply several things we talked about in this slide. We talked about applying datums to surfaces, datum identifications to surfaces, and then we talked a little bit about simulators and how they are used in tooling to make contact with the datum surfaces to simulate the datum surfaces. Now that could be for checking, or that could be for machining. Again, it's a kind of like a tool design thing. So here's how we apply cylindrical features as datums. Okay, so for an axis, apply the datum feature symbol in line with the dimension line that defines the size of the feature. Okay, so in this case we have diameter XXX, and then we have our dimension line, and then extension off of the dimension line, we have our datum call out. Okay, so this is very important because when we align the datum triangle with the dimension, that datum is defined as the feature of size, that diameter. If we were to slide this datum A farther down this way, then that means something completely different. That datum A becomes the surface of the cylindrical feature and not the median center line. Okay, so if your datum is a feature of size, then what you do is you put this datum identificator, you put that right in line with the dimension. And so essentially what you're doing is you're tying it to the size of the part, and you're making clear to everybody that this datum is a feature of size and not a surface. So let's talk about datum targets. Datum targets. This is Objective 3, utilize all methods for identifying datum features, including the use of target points, lines, and areas. So datum targets can be points, lines, and areas, and here's how we call them out. If it's a point, we put it to an X. If it's a line, we put it to a line. If it's an area, we put a border around the area and we shade that area. Okay, so datum target points. Identify the location where the tooling or processing equipment must make contact with the part. Okay, again, we keep talking about this in terms of tool design. You know, datum surfaces defined on a part are typically built into tooling to hold the part, to make sure we have the proper orientation, the proper location, or the proper location's a good word, between the datum features and the parts that have feature control frames that are located from those datum parts. So we use it for tooling. We also use it in inspection media. So spherical ended tooling points are used as simulators. Okay, so if you had a 3-point contact on a surface, you would design bullet nosed tooling pieces to contact the parts in those 3 points. Okay, so each point must have a defined locating dimension. So you need to define all of the points if you're using datum target points. And locating dimension may be basic or have a tolerance. So 3 points define a primary datum, 2 points define a secondary datum, and then 1 point defines a tertiary datum. So how to apply target points. Okay, so near side. On the near side, what we have is would be two isometric views. Excuse me. These would be two views of the part. This datum point is on the near side. We have a solid line from the datum target symbol. We have an X here, and then in the other view, we have an X here to indicate that that X is on that particular surface. Now, when the datum is on the opposite side, then what we're going to do is we're going to dash this line that ties the datum. So that indicates that, yeah, you know, in this view, the target's actually on the other side. Okay, that's indicated by this picture right here. And it would be optional to put the datum, the datum square in that point. I want to talk more about this one in the next movie, but this shows how the 3 points define a primary datum, 2 points define a secondary datum, and then 1 point could define a tertiary datum. So I'm going to pick this up in the next movie.